Hello everyone, and welcome back to this Nanophotonics and Plasmonics class. Today we're going to be discussing about optical interactions. So optical interactions are important in nanophotonics since nanophotonics deal with light matter interaction at the nanoscale. So this light matter interaction depends strongly on the size of your object, your system, as well as its composition or material composition or atomic composition, the morphology, and also the incident light configuration, whether if it's the energy of the incoming optical excitation, the polarization, or the wave vector. Here we're going to be discussing some very general aspect of this light matter interaction, and to lay down the framework for this, we need to mention that because those systems are very complex, the quantum electrodynamics is usually invoked only phenomenologically into a classical framework. So we have a semi-classical framework for those light matter interaction processes that occur at the nanoscale. So the first thing we need to discuss is multipole expansion. So at the microscopic scale, matter is considered continuous. So the charge density, the charge distribution, and the current density are treated as continuous functions of the position. However, when you consider very small objects like just atom molecules or even just quantum dots, for instance, they are discrete. They are composed of atoms. And this atomistic nature of matter is typically not accounted for in the microscopic Maxwell's equations, as we saw in Chapter 2. So, in fact, what we have to do is consider a system which is constituted of individual charges at given discrete positions. So, in a microscopic approach, we need to give up on the definition of this electric displacement and magnetic field, and we're going to be only considering the fields, the E and B fields, the electric field and the magnetic induction, that we later reference as magnetic field as well. And we defined the charge distribution and the current distribution as just a discrete summation of individual discrete charges that are given position at certain locations and with associated velocities, so giving rise to currents. So this is a collective response of individual charges, an ensemble of individual charges, and this is described by a multipole expansion around the center of this distribution or node here. So when we look at the polarization, the macroscopic polarization and magnetizations that describe the behavior of matter, we need basically to account for this discrete discrete ensemble of individual charges, and that's the definition, the expression of the polarization and the magnetization as a function of this discrete ensemble of charges. So the permanent electric potential for discrete charge distribution is expressed as the integral over the volume of the polarization times the incident electric field. So if you substitute the macroscopic polarization by its expression as a function of this discrete set of charges, then you can express the electric potential as a function of the individual charges and with their relative discrete positions and the incident electric field. So you can use the Taylor expansion. As I mentioned, we need to expand that around the center of the charge distribution. So we can use the Taylor expansion around our node that I just mentioned before, which is the center of the charge distribution, which is by convention set to 0 here. And you can expand that into various terms. So just a regular Taylor series expansion around R. And if you sort these, you recognize that you will see that you can break down this in different orders. The first term here represents an electric dipole interaction. So you have basically just a regular charge at the given position that interacts with the incident electric field, and you can express this sum of position times the charge as an electric dipole moment P. So P is an electric dipole moment that interacts with the incident electric field. The second term here is related to an electric quadrupole interaction. So you have a quadrupole interacting with the electric field. You can re-express some of these terms in the form of a quadrupolar tensor. So this is a quadrupolar tensor, which is just the summation of the individual charges times the positions here. So you have a tensor which is going to be interacting with the gradient of the electric field. So while the dipole interaction interacts with the electric field itself, the higher order term of this interaction process interacts with the quadrupolar terms and the gradient of the electric field. And you have, of course, higher order modes. So the dipole interaction depends on the field, as I said, at the center of the distribution. The quadrupole interaction depends on the field gradient at the center of the distribution. So if the field is uniform, because, for instance, you have a very small object, like a small molecule or a small nanoparticle or quantum dot, this gradient of the field will be close to zero. Therefore, this quadrupolar interaction term will be close to zero. Therefore, will remain only the dipolar interaction. So if you have a fairly uniform field across the charge distribution, because you have a small molecule, for instance, or a small nanoparticle, we can use just the dipole approximation and calculate the electric potential only via the dipole interaction term. So something similar can be done for the magnetic potential, V sub m. This is something very similar. You can express the magnetization as a function of the charges, inject that to calculate the potential, expand the magnetic potential with a Taylor expansion. You can have similarly, you're going to have a magnetic dipole interaction term, where you're going to have a magnetic moment interacting with the magnetic fields from the incident optical excitation. You have also an expression here of this magnetic dipole moment. So you see that it's a little bit more complex than the electric dipole moment, but you see that you have individual charges and their position as well as their velocity, because it depends on the current. So far, we've just focused on the potential energy that we just discussed. This VE and VM are just the potential energy. Whether we need to look at exchange of energies as well with the external electric and magnetic fields via absorption or emission of photons. So we need to focus on the total energy, because this is the quantity which is actually conserved in the system. So the total energy is conserved, and in fact it can be described with just a classical Hamiltonian as the sum of the energies from the particle, the radiations, the electromagnetic radiations, and the interaction term. So that's forming the total energy of your system. So let's break down this Hamiltonian term by term. So you do not need to remember the expressions of those terms here. That's useless. When you focus here is the physical meaning of those terms. So the first one is just the sum of the kinetic energy, which is just given here when you have the first time you have the moments. The moments divided by the mass. So this is the kinetic energy of the particle. When we talk about particle here, we talk about the charges, the electrons and stuff like that. And we have the potential energy of each charge. So each electron has a potential energy that you can calculate as we've done just before. The second term is the radiation, the electromagnetic radiations. So this is just the electromagnetic energy. So if you have taken a course in electromagnetism or electrodynamics, this is something which is very familiar. So it's proportional to the volume integral of the field squared, roughly speaking, the electric and magnetic fields. So this is the electromagnetic energy density. The last term of this Hamiltonian is related to the particle field interaction. So this is the interaction, the energy resulting from the interaction between the electromagnetic fields coming from the incident light with your distribution of charges. So whether if it's a molecule or a nanoparticle. So this interaction term can be also expanded into multipoles. We're not going to do the technical details here, but you can expand that into a series of multipoles. So you have multiple terms. The first one is just the charge, the total charge of distribution interacting with the potential, the electric potential at the center of the charge distribution. So if you have a system which is charge neutral, like just a molecule in its regular form, for instance, that's going to be the sum of both protons and electrons. So this is the total charge, the net charge of this particle. Now, if you have, for instance, a charged particle or an ion or a cation, this will be positive or negative. Then you recognize the dipole interaction term here. So the dipole moment, electric dipole moment that we expressed before, interacting with the field at the center of the charge distribution. Then we have the magnetic dipole interaction term with the magnetic moment expressed just underneath. And then we have the quadrupole, the electric quadrupole interaction term, which will depend on the gradient of the fields, and so on and so forth. So you have also a quadrupole magnetic term and other modes that are then very negligible. So when you talk about dipoles, we need to recognize that those dipoles may oscillate also in time. We're gonna have oscillating dipoles, oscillating electric dipoles, and those electric dipoles that are oscillating will actually generate and induce a current density. So this is the expression of this current density for these oscillating dipoles. We have an electric dipole at a certain location, and then this is oscillating with a certain frequency omega, and that's going to generate this current density. So this current density actually can be used as a point source into the Green function formalism that we discussed in chapter 2. So this point source actually will lead to an external electric field, an induced electric field, and an induced magnetic field, taking into account a background electric and magnetic field which comes from an optical excitation, for instance. So you can calculate the induced electric field and magnetic fields from this oscillating dipole via the induced current density via in the framework of Green function formalism. So you can express this, calculate that. We're not going to be doing that here. You can express this very simply. The two fields as a function of the electric dipole P and the Green tensor. So you have the gradient of the Green the curl of the Green tensor on one side, the Green tensor on the other side. So if you look at the case of a homogeneous medium, we have seen previously that the Green tensor can be actually expressed as a function of the scalar Green function here. Just as a reminder, this is the expression of the scalar Green function that we've seen in chapter 2. You can rearrange this. You can inject this scalar Green function into this expression. You can expand all the operators, divergence, and all the operators onto this function. It can take about a page. So actually I'm going to upload all the derivation to go to this to obtain this result here. So you don't need to memorize the result. What is important here is actually to understand the physics behind this expression. So this is the green tensor that will actually provide you with the electric and magnetic fields. So this is basically giving you the dependence of the magnetic and electric fields as a function of the position. We can actually break this down into 3 different regimes. So if you actually expand this green tensor and reorganize a bit of some of the terms, you will end up with 3 terms. You have a near field term, which is basically dependent on 1 over kr cube. So 1 over kr cube. So this is basically what we have here as the near field. So this is a term which is dominant when you're looking at distances that are very small compared to the wavelength of the optical excitation. So very close to the particle itself. You have a second term which is an intermediate field, which is proportional to 1 over kr squared, which is somehow dominant when the distance is comparable to the wavelength of light that you're using, which is basically you have the kr squared here. And then you have this last term, which is proportional to 1 over kr, which is the far field. So this far field is dominant when you're basically looking at the electric and magnetic fields far away from the particle, when distances are much greater than the wavelength of light. So these 3 different regimes, of course, you can continuously go from one to another, but these are basically the 2 important ones, the near field and the far field. When you're close to the particle, the distance is much smaller than light. This is the term that's going to dominate. The far field is the term that's going to dominate when the distance is much greater than the wavelength of light. So you can actually look at a very simple configuration. If you look at spherical coordinates, for instance, which is the most convenient, if you have a spherical distribution of charges, a spherical nanoparticle, for instance, spherical coordinates are very convenient because of symmetries. And in fact, those terms can be reduced. There's a lot of these components that are actually vanishing, and you can calculate, as I said, the electric field and the magnetic field from this green tensor, as we just seen on the previous slide. And in these spherical coordinates, there are only 3 terms that are non-vanishing, that remain. So you have the radial component of the electric field, expanding from the center of the spherical distribution outward. So this is the terms that remain. We have one of the angular component of this electric field, and then we have the other component of the magnetic field. So we have only one component of the magnetic fields and 2 components of the electric fields that are actually non-vanishing in spherical coordinates. That's why this spherical coordinate system is extremely interesting for investigating the near field and far field around the nanoparticle. So if you keep focusing on those terms, so this is the actual expression of the 3 non-vanishing terms for the electric and magnetic field. So let's once again remind that this is not something you have to learn. You don't have to memorize those terms. You just have to memorize and remember what they mean. So the first one, if you focus on that, you will realize that you're gonna have a term which is here 1 over r cubed, and then you have 1 over r squared. So basically you have only the near field term and the intermediate term. So the radial component of the electric field does not contain any far field. So the far field is absent from this radial component. On the other hand, if you look at the magnetic field component, the angular component, you have a 1 over k r squared. So you have the kr here, the r here. You have 1 over k r squared, which is the intermediate field, and therefore there's no near field in this term. So there's no near field present in this magnetic component. So the magnetic component is only a far field. So if you look at what they look like, so if you have, in this particular case, a nanoparticle, let's consider a nanoparticle, for instance, or a molecule, or a quantum dot that has a certain electric dipole moment. This electric dipole moment is aligned along the z direction, so it's pointing upward here. When this electric field radiates, so the electric field which is oscillating here, you have an oscillating dipole moment. The near field, as I said, there's only a component which is radial. The near field will be aligned with the dipole. So you see that the near field intensity distributed on either side, on both sides of the dipole, of the oscillating dipole. So the near field is aligned with this dipole moment. Now, if you look at the far field for the exact same oscillating dipole, so the dipole is still the same. The dipole is still aligned with the z direction here. It's oscillating back and forth. You will see that the far field now, when the distance here is at least of the order of lambda and greater, then we have these additional terms that come in. You have this angular moment, this angular components of the field. Then the field basically radiates on either side. So if you have an electric dipole, then you have those two lobed emissions of far field radiations. So this is a typical pattern for dipole emission into the far field. Like, for instance, if you look at antennas, radio antennas, if you have a dipole radio antenna, they're going to emit in a direction orthogonal to the oscillating dipole that you have. So now let's focus on what the energy looks like for this electric dipole. So you can actually calculate what's the actual average radiated power for this oscillating dipole. If this dipole is oscillating harmonically, you can actually use the Poynting theorem to calculate what's the average radiated power, and you will realize that this is basically proportional to the square of the electric dipole moment. So this is the square of the electric dipole moment times the fourth power of the frequency. So this is something which is important, and that's the dependence in frequency of this dipole moment. So you have much more power being radiated for higher frequencies, and this is increasing with the fourth power of the frequency. Now the rate of energy dissipation in the case of inhomogeneous medium, something we're going to be discussing later on as well, can be calculated as well in this framework, in the framework of Poynting theorem. So this rate of dissipation, of energy dissipation, is basically just how much energy is being dissipated per unit of time, and realize that this is proportional to the imaginary part of this dipole moment, complex conjugate, times the electric field. So this is important for systems such as atoms and molecules in cavities that we're going to be discussing in spontaneous decay just after this. And because plasmonic nanoparticles basically form cavities, every time you're going to be placing molecules near nanoparticles, there's going to be a rate of energy dissipation of this dipole, induced dipole from the molecule, those dipoles from quantum dots, when placed in the electric field induced by nanoparticles, for instance.